Hello friends. So in the previous couple of videos, we have seen the voltage control method of the speed control of induction motor, which is actually a stator side method of control. So today also we will see another stator side method of control, which is called actually the frequency control of the induction motor. Okay, so we are going to control the speed of the induction motor by varying the frequency. Okay, so now basic equation, you know what is the speed of the induction motor. NR is equal to NS into 1 minus S, right? So if you vary either NS or you can vary the value of slip, you can actually vary the speed of the induction motor. Okay, so now to vary NS, you have to know what NS is, right? So NS is equal to 120 into F by P, where F, we can put it as F electrical to show that it is the supply frequency. So you can either vary poles, so that is called the pole changing method. We will discuss it in the end, but that is not a very frequently used method. This method is important. So you can change the value of frequency, that is if frequency changes, okay, the NS value changes, right? The NS value changes. Okay, so when NS value changes and the slip value is constant, NR value will change. So when NS changes, NR will change. NR will change. So this method also you will see finally that this is also coming under constant slip control. Okay, so the slip will be the same, but however you will be changing the value of the rotor speed NR. Okay, so the value of NS minus NR will remain the same. That we will see in the later part of the video. So this is also coming under the slip control technique. Okay, so let's not waste time on that. So frequency changes means what? Okay, frequency changes means frequency can either increase, right? And the frequency can either decrease. Frequency can increase or the frequency can decrease. That is, if for example we take FE rated, okay, FE rated, so the frequency can be either greater than this FE rated or the frequency can be adjusted to be less than the FE rated. Okay, so these are the two conditions. So in this video what we will do, we will see what happens if you actually decrease the frequency. Okay, you are going to see this. That is when the F value, the frequency of the supply is less than the rated frequency. Okay, so in this video we will discuss about the decrease of frequency. Decrease of frequency. Okay. So we will see what happens to the speed of the induction motor when you decrease the frequency. That is, now you are going to decrease the value of frequency. Okay, now you know that there is a simple expression. You know that the flux, okay, is proportional to V1 by F. Right from transformers we have seen these expressions. Okay, so what happens if F decreases? So if F value decreases, what happens to the flux value? The flux value rises. And if the flux value rises, and if the flux value is rising, so if flux value is rising, what it means? It means that I mu is increasing, right? I mu is increasing. From the induction motor no load branch, you can see this is the magnetizing branch, right? XM. And this is the copper loss branch. So this is your I0 value and this is your IC, and this we call it as I mu or I phi also. Okay, so I mu will increase. So if I mu will increase, what will happen to I0? I0 will increase. I0 will increase, and naturally this I1, which is the input current, is I1 is equal to I2 plus I0. So if I0 increases, I1 also increases. So I0 increases, it means I1 also will increase. So now the problem associated with the increase in I mu, you know that we have already seen when we discussed the torque slip characteristics, or in general when we look at the phasor diagram etc. of the transformer etc. You know that whenever the no load current increases, right? Whenever the no load current increases, that is this current increases or this I mu increases, whenever this no load current increases, the theta naught, which is the no load power factor angle, also increases. And when theta naught increases, naturally theta 1, which is the input power factor angle, also increases. Anytime the magnetizing component of current increases, the power factor will actually decrease. That is what we are going to see. It is common for transformers, it is common for induction motors. So if theta naught is increasing, cos theta naught will decrease and cos theta 1 will decrease. Okay, so the effect of decrease of frequency, keeping voltage constant. So in this case we have not varied the voltage, right? Keeping V1 constant. Okay, so what happens? The flux increases, cos theta naught decreases. That means the motor is going to be in low power factor, very low power factor, and cos theta 1 is also going to increase. All these three things, it is not advantageous for us. One, cos theta low power factor means it is a problem in the system. Okay, see, low power factor loads draw a lot of magnetizing current. It is not good for the bus bar to draw such a large amount of magnetizing current in general. Okay, so now if flux rises, what is the problem? So when flux rises, what happens is that, see, the motor goes under deep saturation. The motor core goes under deep saturation. See, usually if you take the flux versus current diagram of a core, so this is something like this, right? So usually it is at this point, in the knee point, the motor will work. But if you increase the flux, it will go to the saturation region. And in the saturation region, what happens? This I naught value increases very heavily to compensate for the increase in flux. See, if you here itself, you can see from here, if you see in the linear region, if you want to increase the flux from this point to say this point, okay, this point to this point, okay. So for example, that flux changes, say delta phi, that is equal to, let us say, arbitrary 2. For that same flux change in the saturation region, from, for example, from here to here, it will draw a much larger current. The system will draw a much larger current. That is why this I naught, I mu will increase, I naught will increase, I1 will increase. And once I naught and I1 increases, cos theta naught and cos theta 1 will decrease. So these are all connected together. So the motor core will go into deep saturation, which is not good for us. And because of all these problems, there is an issue here. So how to solve this problem? Okay, the solving of this problem is to maintain this flux to be constant, right? So flux is proportional to V1 by F, right? So if you only decrease the frequency, the flux will increase. Okay, flux will increase. But what we want to do, we want to maintain this flux as constant. Okay, we want to maintain this flux as constant. We don't want the flux to change. So whatever value the frequency is decreasing, for example, the frequency is decreasing 2 times, you reduce the voltage also to the same value. Okay, so what happens is that, for example, you are having V1 by F, right? V1 by F. For example, you are reducing the frequency to F by 2. Okay, so this will become F by 2. We are reducing the frequency to F by 2. Okay, so I think I told increase in the, I took the example as 2F, I think. No, we are going to take, we are reducing the frequency, right? We'll take it as F by 2. So this V1 also, you convert it to V1 by 2. So what will happen? This 2 and this 2 will go, and V by F will remain constant. Okay, V by F will remain constant, so that the flux is also a constant value. Okay, so to reduce the issues, associated with deep saturation, not to reduce, to eliminate. We are not reducing, we are eliminating the issues. To eliminate the issues associated with the deep saturation of the core, okay, V1 by F has to be constant. V1 by F has to be constant. Okay, so this is very important. Okay, so in this type of speed control, where frequency is decreasing, you use V by F control. V by F control. V by should be constant, so you call it as V by F control, or we also call it as, this is called V by F control, or it is also called as variable voltage, variable frequency control. Okay, so Vvvf control. Okay, usually it is called as V by F control. Okay, so you can clearly see if the frequency is decreasing, what will happen to the NS value? If frequency decreases, see, frequency decreases, NS value will decrease and NR also will decrease. Okay, so for example, at rated speed, rated frequency of say 50 Hz, the induction motor is running at 1480 RPM. If you reduce the frequency, it will go to a speed which is less than the rated speed. Okay, so when you are reducing the frequency and you are using V by F control, the speeds that we can obtain is that NR will be less than the NR rated value. Okay, because you are reducing the frequency from its rated value, any speed that you obtain using this method will be less than the rated speed. So whenever you want to control the speed less than the rated speed, you use V by F control. Okay, we use V by F control. So now we have to go in a little bit of depth here now. So the first equation we have always seen. So V by F should be constant. Okay, so V by F should be equal to constant. V by F should be constant. So for V by F control, these are the things. For V by F control, the first point is V by F should be constant. So this is the first point. That means V1 by F1, okay, where the V1 is the initial voltage and F1 is the initial frequency, will be equal to V2 by F2. V2 by F2. Okay, so this is the condition that you have to follow. Okay, and this is also will be equal to V3 divided by F3, where V3 and F3 are the third iteration of change. Okay, so that is one thing that you have to remember. Okay, now we have to see the next condition. So the next condition that what we have to see is that the electromagnetic torque equation we have already seen. Induced torque equation. Okay, sometimes it's also called electromagnetic torque. So the induced torque equation is 180 divided by 2 pi ns, approximate equation, S into ER0 square into R2 divided by R2 square plus S into X2 the whole square. Okay, so already I have told you, in normal condition, I am repeating this, in normal operation, S value is very less. S value is very less. So Sx2 the whole square will be very less as compared to R2 the whole square. Okay. So in the previous method of voltage control, we took this Ns value also to be constant. But now here Ns value is not equal to a constant. So we have to consider that also. Okay. So we cannot remove that. So this will become 1 by Ns into S into E20 square into R2 divided by R2 square. Okay, we are neglecting this S into X20 the whole square. Okay, so this one term will go and this another term will go. So the torque induced equation you will get to be equal to S into E20 square. I already told you this E20 square is nothing, is proportional to using just transformer action. It will be proportional to the applied voltage V1. So this E20 you can replace by V1. So it will be S V1 square, and this R2 is constant in this equation, right? This R2 is constant in this. We are not changing rotor resistance. So that also we can remove from the equation. It is a constant term. So divided by Ns. But Ns, if you see, Ns is equal to 120 into F by P. Ns is 120 F by P. So 120 is constant and P is also constant here because we are not changing the poles. So Ns will be proportional to frequency. So therefore we can replace this Ns, because we are just not finding the value, we are just putting a proportionality. It will be proportional to V1 square divided by S. So that is one important relation here. Okay. So this also sometimes you can directly use in certain problems. So I'll just keep that also inside the box. But the actual relation that we are interested is that, so the torque induced, so what is slip? You know that slip value is equal to Ns minus Nr divided by Ns. Right, Ns minus Nr divided by Ns. So that also we can substitute here. So this Ns minus Nr divided by Ns. So we can substitute this term here into V1 square by F. Okay. Now you know that this Ns is proportional to frequency. Ns is proportional to frequency. So we can replace this term Ns by frequency. Here. So what you will get finally is that the torque induced is proportional to, see, this is now F into F is F square. Proportional to V1 by F the whole square. V1 by F the whole square multiplied by Ns minus Nr. This is a very, very important relation. Why? Because, for example, the load torque is constant. I have already told you, right? The speed control happens for the constant load torque. Okay, usually it happens with the constant load torque. There are other conditions also. I will tell about that later. But for our explanation now, we will take load torque to be constant. That means for the induced torque to be constant, in this equation for V by F control, the first term has to be constant, that is V1 by F has to be constant. That we have already seen, right? V1 by F has to be constant, okay? V1 by F has to be constant. And that same conclusion we can derive from this expression also. So for torque induced to be constant, V1 by F has to be a constant value. Also, not only V1 by F has to be constant, this also has to be constant. That is, Ns minus Nr should be also equal to constant. And what is this Ns minus Nr? It is nothing but the slip speed of the induction motor. That is why I told you this method comes under the category of the constant slip method. Okay, this is the constant slip method. Okay, so what did we learn? when frequency is reduced less than the rated value, you will get speeds less than the rated speed. Okay, that is the first condition. But if you only decrease the frequency, what will happen? The core may go into deep saturation, no load power factor decreases, and the motor input power factor also decreases. Okay, that is disadvantage. So what is the solution? How much ever you reduce the frequency, that much you reduce the voltage also. That means we are trying to make flux constant. So you are maintaining V by F constant here, V by F constant. So finally I also derived the same conclusion from this equation here, that is V by F has to be constant for torque induced to be constant. Also Ns minus Nr also has to be constant. So here is an interesting thing here. Okay, so now V1 by F1 will be equal to V2 by F2 will be equal to V3 by F3. This is very important for numericals actually. Similarly here, for example, Ns1 is the initial synchronous speed and Nr1 is the initial speed. So Ns1 minus Nr1 has to be constant. For example, you decrease the frequency, so the synchronous speed will decrease. So let us call it as Ns2. So this value has to be equal to Ns2, okay, minus the new speed. That is, the slip speed will remain the same. This will be equal to Ns3 minus Nr3. Okay, so this conclusion is so important that I will put it in the next page here. So the torque induced is constant. So in V by F control, there are two conditions that you have to remember. That is, the V by F value should be equal to a constant value. V by F value should be equal to a constant. That is, the V1 by F1 will be equal to V2 by F2 will be equal to V3 by F3. This is the first condition that you have to remember. Second condition is that the Ns minus Nr also is a constant value. Ns minus Nr is also a constant value. That means Ns1 minus Nr1 will be equal to Ns2 minus Nr2 is equal to Ns3 minus Nr3. Okay, so this is the first frequency, second frequency, third frequency, first voltage, second voltage, and third voltage. First synchronous speed, first speed, second synchronous speed, second speed, more rotor speed, third synchronous speed, and the third rotor speed. Okay, so graphically what happens here actually? So graphically also there is an important thing that you have to remember here. Okay, this is very important here. So you know that there are three equations that we have learned. Okay, so one we have already seen. If you have not seen, go back and watch these videos. So the torque max of the induction motor is proportional to V1 divided by F the whole square. V1 by F divided the whole square. We have seen this already. The torque starting is proportional to 1 by F into V1 by F. 1 by F into V1 by F. This also we have seen in the previous videos. And finally, the slip max is proportional to 1 divided by F. Slip is equal to R2, slip maximum is equal to R2 divided by X2. So these three equations are going to be very important when we are going to see the graph here. Okay, we are going to see the graphical values here. So that is also important. So we can see what is the variation in the torque slip characteristic. In fact, the same topic I have already discussed while discussing variation of torque slip characteristic with respect to frequency. Okay, so in that I think, but we didn't maintain V by F constant. I don't remember that, but almost the same concepts has been covered here. Okay, so now let us see. For example, you're using V by F control. Okay. So in V by F control, you are reducing the frequency, but you are maintaining V by F to be equal to constant. You are reducing frequency, but V by F is constant. So torque max is proportional to V1 by F the whole square. So V1 by F is constant. So if you change the, in this type of speed control, V by F is always constant. Therefore the torque max also will be constant. But the torque starting, you can see, it is not only proportional to V1 by F, it is proportional to 1 by F also. So this term might be constant, but now we can put it as T start is proportional to 1 by F. So this is constant, so it is only dependent on 1 divided by F. So torque start is proportional to 1 divided by F. Slip is already proportional to, slip at maximum torque is already proportional to 1 by F. So now we can see, if you decrease the frequency here, the starting torque will increase. If you decrease the frequency, the starting torque will increase. And also if you decrease the frequency, the slip at maximum torque also will increase. So these two conditions are there. So if you draw the torque slip characteristic, let us draw it quickly here. Okay, so this is the torque induced. Okay, and this is n equal to 0. Here you are having n is equal to ns, nr. Here slip is equal to 1. and here slip is equal to 0. Okay, so we will draw the first torque slip characteristic. Let us say it is as rated value, and we'll call it as a frequency 1. So this is the first torque slip characteristic. Okay, so here you are having the starting torque TST1, and you are having the maximum torque. Okay, so here you are having the maximum torque Tmax1. Okay, and this black line, I will just put it here. This black line conditions are that the frequency is F1. Okay, frequency is F1, V1 is the voltage, and that is the black line. Now let us, what we are going to do, we are decreasing the frequency, right? So if you decrease the frequency, if frequency is decreasing, Ns will decrease. Ns will decrease. So initially this was your synchronous speed. Initially this was your synchronous speed. Let me just take another color. So this was your synchronous speed Ns1. So if the frequency is decreasing, Ns1 will change to Ns2, and this Ns2 value will be less than Ns1. Right? Simple logic here. Simple logic. So now, for example, we are going to draw the second characteristic. So now the graph will start from here. Right? The graph will start from here. So here your this will be Ns2. Okay, this will be the new synchronous speed. And what all are the conditions that we have to follow? The maximum torque will remain the same. So maximum torque will remain the same. However, the starting torque will actually increase. The starting torque will increase. So let us put that point here. So this is starting torque 2. And the third thing is that a slip at maximum torque also will increase. Okay, so that point we'll call somewhere around. So this is the maximum torque. Okay, so this is slip at maximum torque. Okay, so this is SM2 and this is SM1. So you have to have a good understanding of the torque slip characteristics before you come to and watch this video. Otherwise, all these things will go on top of your head. So remember to watch the torque slip characteristic fully, then only you will be able to understand this properly. Okay, so now we are going to draw the second characteristic. Okay, so the second characteristic will look like this. So it will go like this. Okay, and it will be something like this here. Okay, it will be something. So for a particular load torque, I forgot to put the load torque here. So for a particular load torque, say this value here. So we'll just put it in a green color. Okay, so for a particular load torque, let us see the different values here. So this is, and this is NR1. So for the old characteristics, okay, for the old characteristics, that is the black one, where torque load meets the induced torque. This black line is the induced torque. So that speed we can call it as NR1. Okay, the diagram is getting a little bit cluttered, but I think you are understanding. So this speed is NR1. Okay, and for the new graph, which is the red line, so here what is the frequency? The frequency we can call it as F2, where F2 is less than F1. F2 is less than F1. So that speed. So this is the point of new intersection. So this graph you can forget now. This black graph you can forget. So this value is NR2. This value is NR2. So what we have seen is that this difference is here. See, this is NS2. From here to here it is NS2. And this is NR2. So this particular distance you see, that is NS2 minus NR2. It will be same as the this particular distance. Okay. It will be same as this particular distance. That is what we have seen. NS1 minus NR1. That is NS1, which is this value, minus NR1, which is this value, will be equal to NS2 minus NR2. Graphically, it might not be looking very equal because we are not using a scale and doing. Okay. So anyway, I think it is almost close here. So this value here, this value, I'll put in a violet color. So this value will be equal to this value. Now, for example, you further reduce the frequency to F3 value. So if you further reduce the value here, so I'll put it in a blue color. So for example, this is your new value of synchronous speed, NS3. Okay. So for NS3, if you draw the graph, see, this will be the new starting torque, T start 3. Maximum torque will be the same. Maximum torque is same. And here is the slip at maximum torque. Slip at maximum torque. Okay. So the new graph will look like this. Something like this. Okay, it will look like this. So here you are having new intersecting point between the induced torque, which is the blue line, and the load torque. So this is the third intersecting point. And here if you see the speed, it is NR3. NR3. And this is the new synchronous speed, which is starting here. So this is NS3. Okay. So this value here you can see. NS3 minus NR3. See, NS3 is from here to here. NR3 is from here to here. So NS3 minus NR3 is this value here. Okay, so this value and this value will be exactly the same. So that is the basic conclusion. ns1 minus nr1 will be equal to ns2 minus nr2 will be equal to ns3 minus nr3. Okay, and you can clearly see the speed is changing. Clearly you can see the speed is changing. As frequency decreases, you can see that the speed is also decreasing. See, initially you are having nr here, then the frequency speed is decreasing, comes to here, and then further it decreases and it comes to this point. So frequency decreases, speed also decreases. So that is the important point. So in this video we have seen what happens when frequency decreases. In the next video we'll see what happens when the frequency increases. That is another interesting topic. Okay, so till I see you in the next video, it's me Varun signing off, and have a great day. Thank you. Now that the video is over, please stay with me for 30 more seconds. Now the vision of this channel is to create a repository of good quality videos with crystal clear explanation regarding various topics related to electrical engineering. Now if you want to help me spread the word, please share this video with anyone interested in these topics. The second thing is that for me, education is a two-way process. Therefore, if you have any doubts or suggestions regarding any of the videos or regarding the channel, please put them in the comments below. We can have a healthy discussion, and that way we can build a strong community of electrical engineers. So that's it for today's video. So till I see you in the next time, it's me Varun signing off, and have a great day. Thank you.